You know that feeling, right? That lurch in your stomach when an elevator takes off too fast? Or have you ever wondered how a skydiver can just fall out of the sky and land perfectly safe? Well, today we're going to pull back the curtain on the invisible forces that make all that happen. Weight, this thing called apparent weight, and the pretty amazing power of air resistance.
It really does sound like a physics riddle, doesn't it? How can you be falling but not actually speeding up? Stick with me, because by the end of this, you'll not only get the answer, but you'll see just how cool the physics behind it really is.
All right, let's start our journey right here on solid ground, with a force that we're all feeling every single second: gravity, and how it really defines our weight. So, in physics, weight isn't just a number on a scale, it's a force. It's the gravitational force pulling on something. Now, here's something really key to remember. Your mass, which is basically the amount of stuff you're made of, that's always the same, whether you're here on Earth or chilling on the moon. Your weight, though, that totally changes depending on how strong gravity is, which we represent with that little letter G. And what exactly is G? Well, here on Earth, it's pretty much a constant. It's a pull of 9.8 newtons of force for every single kilogram of mass an object has. And it's always, always pulling straight down toward the center of the planet. But, what we call our weight in just everyday life is usually more about what we feel. And this gets us into the really fascinating idea of apparent weight. Okay, here's a common mix-up. A bathroom scale doesn't actually have a little gravity meter inside it. What it's really measuring is the upward support force. It's measuring how hard its springs have to push up to keep you from falling through it. When you're just standing still, that upward push perfectly balances out gravity's downward pull, and that's what gives you your weight. And this is where it gets really fun. The second you start accelerating, that perfect little balance gets thrown off, and the feeling of your own weight starts to do some weird things. Just think about it. You felt this. As the elevator zips upward, the floor has to push harder on you to get you going, so you actually feel heavier. But when it accelerates downward, the floor doesn't have to hold up your full weight anymore, so you feel lighter. That feeling, that's your apparent weight changing right there. So let's just take this idea to the absolute extreme. What happens in that terrifying thought experiment where there's no support force holding you up at all? Yeah, in free fall, both you and the scale are falling at the exact same rate. The scale doesn't have to push up on you at all, so its reading drops to 0. You feel weightless, but, and this is the key part, gravity is still there, pulling on you just as hard as it always was. You're not actually weightless, you're supportless. Okay, so that covers falling inside a nice, neat little vacuum or, a broken elevator. But out here in the real world, when we fall, we have to shove something out of our way, and that something is the air itself. This brings us to our next big player, drag force. You can just think of it as air friction. Anytime an object moves through a fluid, and yep, air totally counts as a fluid, that fluid pushes back, and it always pushes in the opposite direction of the motion. And this force isn't just one set number. It depends on a few things. The faster you go, the stronger the drag gets. The bigger you are or the less streamlined your shape is, the more drag you're going to create. And of course, trying to move through something thick like water creates way more drag than moving through thin air. I mean, the parachute is just the perfect example of this in action. It's a brilliant piece of engineering with one single job: make as much drag as humanly possible. By blowing up an object's size and shape, it creates this huge upward force that fights back against gravity. So, now we've got these two forces in a fight: gravity pulling down, drag pushing up. What happens when these two titans of physics finally go head-to-head? Well, it happens in a few stages. Right at the beginning, gravity is the undisputed champ, and the object picks up speed like crazy. But as its speed goes up, that upward drag force gets stronger and stronger and stronger, and then, eventually, it gets just powerful enough to perfectly match the downward pull of gravity. The forces are completely balanced. And that, right there, is the answer to our very first question. When the total, or net force on that object hits 0, it stops accelerating. It's not speeding up anymore. It's still falling, for sure, but now it's at a constant maximum speed. And we call that terminal velocity. Now, what's so cool here is just how different that top speed is for different objects. A light little table tennis ball with a big surface area hits its terminal velocity at only about 9 meters per second. But a dense baseball, it gets up to 42.
And a skydiver, in that spread eagle pose, trying to catch as much air as possible, tops out around 60 meters per second. That's almost 135 miles an hour.
So, you see, from just standing still, to accelerating at an elevator, to falling at your absolute maximum speed, it's really all just a story about the balance, or the imbalance, of forces.
Let's just wrap it all up. When you're at rest, the net force is zero, and what you feel, your apparent weight, is your real weight. When you're accelerating up or down, that apparent weight changes. In free fall, when it's just gravity doing its thing, your apparent weight is zero. And then, at terminal velocity, the forces are balanced again, the net force is back to zero, and your apparent weight actually feels like your real weight again. If you need a super simple way to remember how drag works, just picture this. You're trying to run through a really crowded hallway. The faster you try to go, the more people you bump into, right? That resistance from the crowd naturally puts a limit on how fast you can possibly go. That's pretty much drag force in a nutshell.
And that kind of leaves us with one last thing to think about. We just saw how a simple change in body position, from a dive to a spread eagle, can completely change the forces acting on a skydiver. It really makes you wonder, doesn't it? What other powerful, invisible forces are we influencing all the time just by the way we move?